Phys2212 Lab 3. Lab instruction. The purpose of this lab was to use the principles of energy conservation to predict the behavior of circuits containing ohmic resistors and capacitors in series and in parallel. Model/fundamentals. Kirchhoff's node rule, Kirchhoff's loop rule, capacitance, steady-state vectors, Ohm's law, V equals IR, and the conservation of energy. Lab introduction, results overview. Using a multimeter in the experiment, we found a current of 0.0196 amps, a 47 ohm resistor voltage drop of 0.921 volts, a 100 ohm resistor drop of 1.96 volts, and a voltage summation of 0.119 volts. A time in for our light bulb in the capacitor circuit was 13.3 seconds. Using Kirchhoff's loop rule, the conservation of energy, and Ohm's law, we have a true current of 0.02 amps, a 100 ohm resistor voltage drop-off of 2.04 amps, a 47 ohm resistor voltage drop-off of 0.96 amps, a voltage summation of 0 volts, and a time to dim of the 10 ohm light bulb in 10.986 seconds, which was calculated. Assumptions/sources of error. First, the system was the circuit components exclusively. The surroundings was everything else in the universe. The first assumption/error was that no charge was lost from handling the capacitor. The second error was that the resistors ohms were perfectly calibrated to the desired amount. The third error was that the battery voltage was perfectly calibrated to be the 3 volts we were looking for. And then the last assumption/source of error was the capacitor was perfectly calibrated to the correct capacitance in the correct farads. Experiment initial setup. The experiment involves setting up and analyzing circuits. First, a simple series circuit was made using two 1.5 volt batteries, two resistors, 47 ohms and 100 ohms respectively, and two ammeters to measure current. That ammeter was converted to a voltmeter and differences were measured. Next, a resistor capacitor circuit is built using a capacitor and 10/20 ohm light bulbs to observe capacitors charging and discharging behavior, with measurements recorded to analyze voltage loss over time and measure the current with a conservation of energy. Here's the experiment. We can see all of the necessary circuits we need for this experiment. Experimental data. Current in the dual resistor circuit was 0.0196 amps. This current will not change as long as the resistance remains constant. If the resistors were in parallel instead of in series, this current would be greater. Voltage from the 47 ohm resistor was 0.921 volts. Voltage from the 100 ohm resistor was 1.96 volts. The voltage sum was 0.119 volts, which is not equal to our assumed 3 volt battery. Time for a 10 ohm light bulb to stop shining was 13.3 seconds. Here's the model/code for the experiment. We did this modeling in PhET, and you can see from our experiment, we start out at 0 volts, we go to 1.5 volts with the first battery, then up to 3 volts, as we remain constant at 3 volts until we hit the first resistor, which then we drop by the calculated amount, and then we stay constant until we get to the second resistor, until we drop back down to 0 volts for the rest of the circuit. Here are the model calculations. Our formulas were the voltage of the capacitor as a function of time, which is number 1. Our second one was Ohm's law, V equals IR. And our third formula was the loop rule, which is the summation of voltages will equal 0. Using Ohm's law, we could find the current in the dual resistor circuit to be 0.02 amps. Our voltage from the 47 ohm resistor, also using Ohm's law, to be 0.96 volts. Our voltage from the 100 ohm resistor, also using Ohm's law, would be 2.04 volts. And our summation of voltages, which we can check by the loop rule, will be the 3 volt battery minus the voltage drop-offs from the resistors, which will equal 0, which means that the loop rule holds true. We can then also model our light bulb turn-off as a voltage from the capacitor. We can take the natural log of both sides to get this voltage drop-off as a linear function of time, and we can see that it takes 10.986 seconds for a 10 ohm light bulb to turn off with our current capacitor. Questions? What if you charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery and the ammeter. Discuss why the measurement time is different from the predicted time. Our model would predict the capacitor to reach full charge instantly, since there would be no resistance. However, with our ammeter, we saw that this is not correct, and it still takes time to charge the capacitor. This is because in the real world, the wells we have resistance that we did not account for in our model. Discussion/conclusion. Series circuits can be modeled using Kirchhoff's rules and Ohm's law. Capacitors can store charge based off their capacitance value. Capacitors' charge can act as a pseudo battery in charge circuits. And multimeters can be used to measure amps, ammeters, and voltage. Thank you.